Okay, so chapter 34, we're going to do 4 problems. The first one I want to do is problem 7. So problem 7 says a concave shaving mirror has a radius of curvature of 35 centimeters. It is positioned so that the upright image of a man's face is 2.5 times the size of the face. How far is the mirror from the face? So this is the mirrors. You have an object that's in front of the mirror and informs the image, and so several key things that we can deduce. One is that the radius of curvature is 35 centimeters, and it is a concave mirror. So for a concave mirror, we know that R is positive. The radius is positive. Concave mirror is 35 centimeters. Okay, so your F, the focal length of the concave mirror, will be half the radius, which is 17.5 centimeters. Okay, so when we're dealing with the chapter 34, we're going to keep the unit as in centimeters. Okay, and it says that the face is positioned so the image is 2.5 times the size of the face. So in other words, if you remember, we have the magnification. Magnification is has two expression. One is the image height over the object height, and also that's equal to negative I over P. Okay, so in this case, we know that the magnification is 2.5. So we know that that's equal to 2.5. So this equation relates the image distance to the object distance. So in that case, your I is equal to negative 2.5 times P. Okay. So once we have that, then then we have the focal length, and we have the I in terms of P, so we can apply the equations. 1 over I plus 1 over P, that is equal to 1 over F. So in that case, we can just plug in the numbers. So your F, so your I is negative 2.5 P. So that's negative 1 over 2.5 P. And then plus 1 over P, and that is equal to 1 over 17.5. So once you plug in the numbers and then rearrange this, to get your P, you should get your P with a value of, let me see, 10.5 centimeters. Okay, so that's this is basically how you would do it. Several key things here. One is that radius is given, and because this being a concave mirror, so your R and F are both positive, and you have the 2.5 that relates the image distance to the object distance, and there's a negative sign in front of it, so your R is equal to negative 2.5 P. Okay, so that's basically how you would do it. Do this, so it's not that, so should be very straightforward. And the next thing I want to do is that I want to do the two lens system problem. So the next thing the next problem I want to do is problem 80. So you can read the problem later, but suffice to say that the P here indicate the object distance, and the lens one has the focal length of 15. C indicates convergent lens, and the separation D is 10 centimeters. And for lens 2 is also convergent lens and has the focal length of 8. So you want, based on this information, you want to find out, what is the final image, and what is the lateral magnification, and whether it's a real or virtual, whether it's upright or inverted, and which side, where is the image, the final image is located. Okay, so based on this information, we want to work on the problem. So let me just do this. Problem 80. All right. So so here's what you want to do. P1 is given. Okay, so I'm going to redraw the, so I can just use this. So I have my first lens, okay, and my F1 is 15, and my second lens is convergent again, and it has the focal length of 8, because both are convergent, so focal length is positive, okay. And then the object distance and the separation here is 10 centimeters. And then you have the object distance, which is 10. So let's say this is 10. Okay. So then, so this I will call that P1. So our first thing is that ignore the second lens. Let's just look at when you have an object that's 10 centimeters in front of the first lens, where should that image be formed? So you will apply 1 over I1 plus 1 over P1, and that's equal to 1 over F1, okay? And so your F1 is positive 15, your P1 is positive 10 because it's in front of the lens. So based on this, you should be able to calculate your I1, and you will get an I1 value. Let me see. So you will get an I1 value that is negative 30. So it is negative 30. What does that mean? It means that because the image distance is negative, it means that it's a virtual image. If it's a virtual image, it will have to be formed on the same side where the object is. Okay. So so this is 10. So I'm going to, so if this is 10, then let me draw the line here. So your and then so this will be where the I1 is formed on the same side, and also it is virtual. And so in order to decide the orientation, you will use this. First of all, calculate M1 the magnification. So magnification is negative I1 over P1, okay. And your I1 is negative 30. So negative, negative, that becomes positive. So you have the 30 in the numerator, and in the denominator, you have 10. So you will get a positive 3. So if the magnification is positive, it means that the object, the image will have the same orientations as the original. So original, you have the, you have orientation like this. So you would expect that it's 3 times large, and it is located upright position like this. Okay, so this is your I1. This is where the I1 is, but that's not the final image. So based on this, so the image of the image that's produced by lens 1 becomes the object of the second lens. So then we can apply the lens equations again, ignoring the first lens, and just treat this as my P2. Okay, so this is my P2. So from P2, from this point all the way to the second lens, we need to decide what is our P2. So this is already 30. Okay, that's your I1. And then here's additional 10. So your P2, you have 30 plus 10, that will be 40 centimeters. Okay, so you apply 1 over I2 plus 1 over P2. That is equal to 1 over F2. And your F2 is 8, your P2 is 40. So based on this, you can calculate your I2. So I get my I2 value. I will get my I2 value that is equal to positive 10 centimeters. So the sign, again, the sign here tells you that it is a real image because it's positive. So the final image, which is I2, you will get a real image. So it's a real image, okay, based on the sign. And where should it be located? If, based on this lens 2, if I2 is positive 10, it means that it has to be behind the lens, okay? So this will be your I2. Okay, so that's your I2. Now let's look at the orientation. To calculate the orientation, you would say M2, that's equal to negative I2 over P2. Okay, and your I2 is positive 10. So we have negative 10 over positive 40. So your M2 is negative 0.25. Okay, if it's negative 0.25, it means negative indicate that the image is flipped compared to the this object. So it is flipped. So it'll be like this. So this is I2. okay, with that. So this is that. So M1 has the magnification 3, M2 has a magnification of 0.25. So we can calculate total magnification, which is M1 times M2. So the final answer is that your total magnification is negative 0.75. Okay, and that will make sense. Why is it negative? Because originally you have the upright and the final image is actually inverted, is flipped. So compared to the original object, it is it is being flipped. Okay, so that's basically how you do this kind of problem. So the final image is real, and it is on the behind the lens, behind the second lens, and with the total magnification, so 0.75 negative. And also if we know that, say, this is the height of the object, which has h, and then the final image has the height of h prime, then this can also be calculated using with the absolute value that is equal to the h prime over h. Then you can calculate what is the final image height just based on that. Okay, it is not, it didn't ask, this problem did not ask you about the height because it's not given. But just so you know, if you were asked to find the image height, this is basically how you would do it. Okay, so you can see that this is this is how you apply the lens equation for two lens system. Okay, so we're going to continue to do another one, problem 83. So let me erase this first. And then let me just go down. So problem 83, we have the object, which is at 20. And the first lens is a convergent lens with a focal length of 9. The separation of these two lenses is 8 centimeters. And the second lens is also a convergent lens with a focal length of 5. So then based on this, we want to find, we want to do the same, do the problems. So, so that's draw the diagram first. Okay. So we will have first lens, F1 is 9. Second lens, well, this is actually, I don't want that. 12. Oops, already. So the second lens is convergent. So you have your F2, which is 5. And the separation here is 8. Okay, and the object distance is 20. So this is your P1. So again, what you're going to do is apply the lens equation. So I'm going to start from here. So you have 1 over P1 plus 1 over I1. And that's equal to 1 over F1. Okay, so F1 is 9 and P1 is 20. So when you do this, you should be able to calculate I1. Let me see. When you do this, you will get an I1 that is equal to 16.37 centimeters. So it is a positive, meaning that the first image produced by the first lens is real. If it's real, which means that it has to be behind the lens on the opposite side where the object is. This is 8, so it has to be somewhere here. Okay, so that this from this position to this place, that's 16.37. And let's look at the orientation. So you calculate your M1. Your M1 is equal to negative I1 over P1. Okay, because I1 and P1 are both positive, so your M1, you should get a negative value, which is negative 0.818. And this indicates that the image is is smaller and it's negative, which means that it's inflicted, is flipped, inverted. So this is where your I1 is. Okay, all right, and then so your I1 now becomes your P2, the object distance of the second lens. So this one being behind the lens. So by default, it is actually negative. So we need to figure out what is the separation between this point and the second lens. This is, the total is 16.37, and from this point to that point, and this is 8. So the difference here will be 16.37 minus 8, so that'll be 8.37. Okay, so 8.37 is your P2. And so we're going to apply, the lens equation again. So you have the 1 over I2 plus 1 over P2, and that must be equal to 1 over F2. And your F2 is 5. So once you do that, you'll get your I2, and your I2 would have a value. You see my I2, you would have a value of positive, again, 3.13. So that positive value of I2 indicate that the image, the final image is real, okay? If it's real, then, and then we're going to calculate the M2 to see the orientation. So your M2 is equal to negative I2 over P2, okay? And because your I2 is positive and your P2 is also, and your P2, your P2, all right, we said that, let's backtrack. So this is your P2, all right? This is where the first image is, and the first image counting from the first lens is 16.37, and then there's an A between the two lenses. So this distance is 8.37, but that's not your P2, because your P2 is actually behind the lens. So your P2 is actually negative. Okay, I forgot to say that. So your P2 is actually negative because it's behind the lens instead of in front of the lens. So then when you plug in the negative 8.37 and then your F2 is positive, F2 is positive 5, and then you will calculate your I2, which is a positive 3.13. Okay, so in that case, when you plug in this, so negative, and then this is 3.13, and then your P2 is negative 8.37, you will get M2 that is actually a positive value. So M2 is positive 0.374. What does that mean when M2 is positive? When M2 is positive, it means that the final image has the same orientations as the object. The object is this. This is your P2. So your I2 will have the same orientation as that. And because it's a real image, it has to be on the opposite side where the object is. So your I2 will be somewhere here. So that is your final image, which is located between the two lenses. Okay. Now, what about your total magnification? Your total magnification is M1 times M2. So your M1 is negative value. Your M1 is negative value here, and your M2 is positive value there. So when you plug in the number, you get your the total magnification, which is negative 0.306. So what does that mean? That's negative. It means that the final image in reference to the original object, is being flipped once. Okay. So so this is basically how you apply the lens equation. So the tricky part is that this one, the P2 is negative because it's behind the second lens, and your I2 is positive, meaning that it's a real. So it has to be in the opposite side where the object is, just so that light can actually converge at that point for the image to be formed. Okay. So that's your 83. And then the next one I want to do. The next one I want to do is 87. So previous two examples are the two lenses, then both lenses are convergent lens. So I want to do 87. This still with two lenses being divergent lens. So divergent lens, you will apply the lens equation as usual, except that the focal length now is negative. So you have, this is a central axis. So you have the first lens, okay, with F1. Your F1 is now negative 12. And then your the second lens has the focal length that is negative 8. and the separation between them is 10. Okay, that's your D. And the object, is located 20 centimeters. So that's your P1. So you proceed as usual. So you have the 1 over P1 and then plus 1 over I1. That's equal to 1 over F1. And your F1 is negative 12. And your P1 is positive 20. So based on these numbers, you should get your I1. You should get your I1 that is equal to negative 7.5. The negative here, when I is negative, it means that it's a virtual image. If there's a virtual image, it has to be on the same side where the object is. So, and then that will be located 7.5 in front of a lens. So this is your I1, okay? So then let's look at the orientation. So your M1 is equal to negative I1 over P1. And because R1 is negative, so negative, and then P1 is positive, so you will get a positive value. So M1, you will get 0.375. So M1 has been positive, it means that it has to have the same orientations as the original. So this is where your I1 is, and it's smaller. Okay, so this is your I1. And then your I1 becomes the object of the second lens. So ignore the first lens. This is 7.5, and then this is 10. So altogether, this P2, this is also where the P2 is located, is this. So P2 will be 7. So your P2 in this from this diagram, that'll be 7.5. Add to the separation, which is 10. So your P2 will have a value of 17.5. Okay. So once you have that, then apply the lens equations again. So you have the 1 over P2 and then plus 1 over I2. And that's equal to 1 over F2. So when you do that, you should get your I2. You will get your I2 value that is negative 5.4 noise. So this being negative, meaning that your image again is a virtual, okay, and it has to be on the same side where the object is. Remember, we're talking about the second object, so P2. So on the same side, and that'll be 5.4 noise. So it will be somewhere here. So this is your I2. Okay, so your final image is virtual, and it will be in front of the second lens. And then let's look at the orientation. So that's use M2. So M2 is negative I2 over P2. Because I2 is negative, so negative becomes positive, and P2 is positive. So when you plug in the number, your M2, you will get an M2 that is positive 0.31, meaning that you will have the same orientations as the object. So it will be like this. So this is same orientation. We can calculate total magnification, which is M1 times M2. So the final answer is that capital N, you will get 0.117. And your capital N being positive, meaning that the final image and the original object, they will have the same orientation. Okay, so so this is basically how you apply the lens equation when you have the two lens system to find out where the final image is formed. All right, so that's basically how you do this.